We have two papers in this section. Amit Kumar is going to present his paper on reinforcement learning driven information seeking, a quantum probabilistic approach. Then we have another paper by Steven Zimmerman, Stefan Herzog, John Chamberlain, David S. Weiler, and Udo Kruszwitz. These are two full papers, so half an hour each. So I think we can start. Amit, are you ready?
Yeah. Hi everyone. I'm Amit Kumar Jaiswal, and I'm a PhD student based in the University of Bedfordshire. And our work is supported by the European Union Horizon 2020 project Quartz. So today I'm presenting a work in progress work, uh, which is basically how we can uh, combine the idea of foraging for information seeking task in a principled framework to describe the user experience basically for in his information seeking task. So so I'll go through first with the background of the work, and then what we're doing new here, and we take a brief overview of reinforcement learning and IFT, and we also differentiate between these two and how it could be, how can the information foraging theory can be combined in a framework to delineate the information seeking behavior. And then we incorporate the uncertainty that we talk in this uh, in the paper using a quantum probabilistic framework, and then we conclude with the work. So the uncertainty in information seeking in our paper is basically closely related to the user's information need. So there are many uncertainties in information seeking depending on the situation. Um, it, it, it could be so, and the thing is that we consider information seeker as a forager uh, from the previous work of VTech. So they did some similar information seeking task related task where they found that the forager behavior is more like a kind of a seeker. So we use those inspiration, and the training field of reinforcement learning has emerged as a good way to represent how we can represent the user action and their dynamic transformation, simultaneous transformation of action from one state to other, or many actions in a state. And the uncertainty in users information need is basically we dealing with let's say a user pick a document, and there is another document that has an equal chance of um, relevancy, like 50-50 probability. So the user going to a situation which is ambiguous to decide which document is exactly relevant for him. So we tackle on that. We tackle on the basis of such sort of uncertainty. So so what we're doing here is we basically consider information seeker as forager, and we try to model the exploration of a seeker by means of forging behavior in a reinforcement learning framework that is basically driving an agent using the foraging behavior, and we assume of the uncertainty which is related to the user's information need. So we we follow the constructs from uh, quantum like IR models, basically quantum language models, to represent those user actions and combine it in a theoretical framework so that we can guide such uh, foraging behavior for information seeking. So why do we need reinforcement learning? So reinforcement learning is basically so in general, human transfer information to other animals in a, it is a common method of learning, and which is generally called reinforcement learning. Why we need so reinforcement learning is one class of machine learning which is neither supervised nor unsupervised. So there is no supervision. It drives on it expect only a reward, um, whatever it learns through the environment and by experience. So so there are some drawback of the reinforcement learning, like is the feedback they do have for the agent is basically they learn from interaction with the environment, so it's kind of experience. So the feedback is delayed, is not instantaneous. And so in reinforcement learning, it it learn user behavior, not uh, from data. This is common in machine learning. So the central idea of reinforcement learning is that it interacts with the an agent interact with the environment, and it learns from experience, and they expect to maximize their reward. And in IFT, the user or any kind of forager could, I mean, in IR we take searcher as a forager. So a searcher basically search through the environment, but it go up from patch to patch. So it's kind of a sequential, and it learns from enrichment. So enrichment is a strategy, uh, which could be a user interaction or the search behavior, and the forager wants to maximize as much as consume as much as information in little time. So here we take the inspiration from a previous work that uses Markov property to describe user search process in an interactive information retrieval system. So basically, they did a eye tracking experiment to evaluate such a method of Markov chain for user search process. So in their situation, they basically is completely based on the Markov decision process. So this was from the Tran and Norbert's team in 2012. So we take the inspiration that how we can draw such user process or Markov chain in principal framework. So we see that in reinforcement learning, we do have the same sort of there are some principal construct that we can combine to have a unified framework that can delineate such user search process. And from Markov property, it says that the future is independent of the past given the present. So in foraging, if we see the how the information foraging behavior or how the forager works, so it basically um, it starts from one patch and end up with the like the next patch, but it starts from present. It don't learn from their past basically. So we try to combine such sort of property in that we can delineate foraging behavior. And in reinforcement learning, we have the agent and we want to simulate the agent foraging behavior. So so the main so the idea of reinforcement learning is basically an agent, which is a user. So it basically gives an action, so it may give a query, or it can start, and then it starts clicking to a link, or maybe it could be document or video or whatever the information content, and then the environment feedbacks. So the environment gives a reward, and on the other hand, it gives so let's say if a user click and then it starts exploring, and then it move back to the search engine, and it may perform another search, or it may reformulate the query. So so this observation, the blue arrow, it basically is saying observation. So this is basically state. So but we can separate these two in or we can combine in one way depending on the task we're tackling. So this is basically to denote the mental state of the users, what he's thinking about the 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 information that he's exploring. So we basically interpret the right part in this on the left, that how our reinforcement learning scenario runs. And so the information foraging theory is basically is a theoretical framework to describe information retrieval behavior, and it is basically rooted in the rooted in the ecology and is derived from optimal foraging theory. So the theory it is a theory to understand how humans seek information, and how it learns from experience. So and so there are many there are many recent works that uses information foraging theory to tackle some of the retrieval tasks, basically user search behavior mostly. And the IFT has three main models, which it uses a construct to drive the uh, the theoretical framework, that is information patch, information send, and information diet. So information patch in a web search could be a document, or a topic within a document, or snippets, or labels. And information set is basically it gives that how a user make use of those perceptual cues, that it can go from one snippet, that is patch to patch, and so it gives a way to move from one patch to another patch. Information diet is it allows the users to narrow or expand their diversities in information sources based on the profitabilities. And so here we combine the foraging behavior in a reinforcement learning agent that we call as reinforced foraging. So the hypothesis, as we said before, is the information seeker is forager, and that is assumed as a reinforcement learning agent. So we also bridge the gap of reinforcement learning, the limitations of reinforcement learning. So in reinforcement learning, a user or a or agent can't explore and exploit at the same time, but in foraging we do have exploration and exploitation at the same time. So this trade-off, if we uh, com- feed such foraging behavior in a reinforcement learning agent, then we can bridge this uh, limitation. We can resolve this limitation, and we call it as an adaptive oral agent. So, and it also uh, somehow um, solves the problem of delayed reward. So why every step of seeker is important. But in foraging, it is a sequential behavior from one patch to another, and to the second patch to the different patch. So we also figure out the idea of delayed reward via information foraging theory. So how we apply this reinforced foraging to information seeking. So in reinforcement learning, it says interact with the environment. In information seeking, it says the process of seeking may provide the learning required to satisfy one's information need. So in reinforcement learning, they don't have a uh, uh, grounded mechanism that how you interact with the environment. So you can interact in any way. But we in seeking we have uh, a user may be provided with uh, some, or it come up with some information need, whether it is vague or confined. So so we we somehow relate the reinforcement learning, the idea of experience in reinforcement learning, to this seeking. And so so we consider the available actions. So available actions means the user actions that are performed by the user, but it didn't result in a relevant information. So we consider that available actions as exploration. So action in our work refers to a user query, and exploitation here we refer to a positively rewarded action. So the query that uses input and get positive relevant result based on the reward, a positive reward. So and this information seeking behavior also meets the trade-off that has been done in the previous work. So we considered that such behavior in using IFT is mostly sequential. So we use the framework of quantum probability. Why do we need probabilistic framework to to tackle the task of uncertainty, for in a user's information need for this seeking task? So let's say, so this is a so the quantum probability theory is based on a Hilbert space formalism. So what is Hilbert space? So in quantum mechanics, we represent the physical state of a system using a vector. So the Hilbert space is an abstract vector space that is that possesses all um, that possesses such behavior to such a way to represent uh, these information needs. So let's say we have a document, and we have a D1 and D2 document in D. So basically, these D1, D2 are basis vectors, and let's say if it combines, so if it combines, and we don't know whether this D1 or D2, so it has an equal chance and it is equally relevant. So the user don't know which one we have to pick. So we represent superposition state to represent this, and this row basically refer to a density state. So what we have is we doing um, um, representation for many documents so here. And how we can perform the projection. So this is, so if we measure this length of the superposition state vector, so we can perform the projection. We'll talk where we use projection. So the constructs that we formulated in our framework is are in this follow way. So the agent in our framework is a forager, the information seeker. The action that the agent performs is a query, and those are multi-turn queries. So it could be for any task like query formulation. So basically, we want the user to go into a interaction loop. So and this environment delivers observation or state in another state after receiving the user's actions, that is queries. And state in our framework is basically we perform representation based on the local and global projection. So we talk in the next slide what exactly is that state in our framework. So and the state transition is so let's say you perform some two, three actions or many actions in one state and jumps to other state. Like let's say it completely changed the query and looking for some different information. So we how we measure such state transition. So so that is and we also have a dedicated policy network that is in reinforcement learning that we use to reflect the merit of the agent, especially we'll talk what exactly it is. We're using actor critic network basically. Um, so the reward here is a success value of an agent's action, whether that action is uh, relevant or not. So our framework basically so it has a agent and the environment part is on down. So this environment basically contains documents, as we call it as information space. So the agent inputs these many actions. So it could be one or it could be many, but we basically deal with the many actions. So these are queries. So and these are different states. So this basically observation, but we call it as a state. So we can separate it out, but we don't consider the user beliefs state or the mental state here. So we consider it only as a state. So so there are many queries that user inputs, and so these are for direction. I mean, we 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 want to we're just trying to make it easier to that how the user actions go into the environment, basically in the search environment. And we perform a local and global representation. So these local and global, so these are basically direct notations that we use from Hilbert space formalism. And the local representation is basically, so whenever once input a query, so the agent inputs a Q and query, so we do a local representation of only the current query that has been input. And the global representation of a query is the representation of unseen words that has not been input but is in the training data. So so the current query, so we perform a local, we represent the local representation, uh, local distribution of the current query, and the global representation of all unseen words or compound meaning. So yeah, it means a query. So we do a global representation, and then we perform projection from global to local. We call it as we use inner product to perform the projection, and then it results in a higher dimensional tensor. So using tensor operation in the Hilbert space to represent a query by tensor product of words. And after the projection, we use a basic convolutional neural network to 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 deal with such a high dimensional tensor, because the probability amplitude that we get is is very of is very high. It has a very high dimension. So we use the CNN layer to so that we can um, solve the high dimensional problem. And then we map the each of the unit vector that we get from the global projection to the query, and that mapping is basically the state. So this we call it as a product pooling in our paper. We use a dedicated mechanism to calculate the state, and this actor network outputs the action. So the actor and critic network is basically policy mechanism in reinforcement learning that is based on the policy and value based network gradients. So this actor and critic networks works in a way like, let's say we have an example like that a son and mother. So the mother acts as a critic and the son acts as an actor. So mothers give uh, uh, um, some directions, or it's some so the mother gives direction to his son that what is being correct and what is wrong. So this critic network acts as a mother, you can say, as an analogous, and this critic network reflects the merit of the action generated from the actor network. So this is basically, you see that there is a reward out of this. So we input this state and this actor state and the action that is output from that is the output of the action network. We take as input in the critic network, we then represent in a complex lookup table. So this mechanism has been used from a previous work we refer in the paper from complex embedding that we call. And we have three types of rewards. So that is a positive, negative, and zero. So plus one, minus one, and zero. So plus one is means relevant. So it's a relevant match of a query for a document, and the negative means is a mismatch, perfect mismatch, and the zero means um, partial match. So this critic networks basically gives the reward, and we use the reward for the action whether that action is relevant or not. So we reflect the merit of the action that is generated from the actor network. So the contribution of our work is, we use a reinforcement learning framework that is parameterized by uh, quantum language model constructs, uh, and incorporates the information forging behavior for the information seeking task, so that we can model the experience in a formal way for IR tasks. So and uh, and the policy network that we use in our reinforcement learning framework is actor critic network. The conclusion of work is, so we basically took a first attempt to incorporate a foraging behavior in a principal framework for reinforcement learning, and how we can characterize such seeking behavior in a behavioral reinforcement learning model that that needs uncertainty of those users' information need. Thank you.
Okay, thank you, Amit. We have time for a few questions. So, question time.
Yeah.
Any questions? So I have a question while the attendees are trying to formulate some questions. So there are at least two pieces in your work. One is to parallel reinforcement learning and information foraging theory.
Mm-hmm.
So, and the other piece is related to how to estimate and the probability space to deal with the uncertainty
Mm-hmm.
of the decision processes. I am interested in understanding better the parallel between information origin theory and reinforcement learning,
Mm-hmm.
because it's a nice connection. So I understand that for you, the forager is like a user or an agent interacting with the system. So, but what are the similarities? What are the differences between the two theories?
So in reinforcement learning, in reinforcement learning and information foraging, so we have agent in reinforcement learning, and we have forager in information foraging. But if we consider information foraging theory, that is from information retrieval perspective, and in reinforcement learning, they do have an agent, but that agent keeps on learning from present to the future, right? So, or to the next step. But they don't have any formal way that agent adopts the environment to interact. So they can interact anyway. They don't have any medium. So we can't say sequential, we can't say nonlinear or anything. It depends on the situation. So there is no a formal mechanism for a reinforcement learning agent. But in foraging, a forager can forage, can move from one patch to another in any way, but it has a sequence. It has a sequence like patch to patch. So we do have a mechanism in foraging that is, it's kind of a sound mechanism that how a user can perform foraging or searching basically. So it is mostly similar to in information retrieval or web searcher we can relate with the forager. But in reinforcement learning we have a different situation because the agent uh, have no formal way to run through the environment or learn from whatever it gets in the environment. So it has no mechanism. So we try to bridge that, we try to solve those problems in reinforcement learning. So if we incorporate the forcing as an agent, then of course that agent can of course can move from one patch to another. But then we have another problem because in reinforcement learning we can't do a simultaneous exploration and exploitation. So if we borrow something, if we borrow the concepts from foraging, information foraging theory, they do have a simultaneous exploration and exploitation. So we can solve this trade-off in reinforcement learning if we adopt from foraging. So
Okay, thank you. We have one question in the chat. Can you
yeah,
can you open it?
yeah. Uh, Sorry.
So why quantum probability, basically?
So yeah, it's a very good question. So give a second. So it's a very good question. So why do we need quantum probability? So this is a work by Peter Vitek in 2016. So they did a information seeking task. So they did a study using the designer interface, and they perform eye tracking. They use eye tracker to perform the seeking task, and there they found that the forager comes with a situation where the information that users select, they come with a uncertainty which has two aspects. So there's a risk associated with that selection of the information. It could be document. So the document is is in risk for the searcher, whether it has a risk associated and whether it is ambiguous. So risk and ambiguity happens at the same time. So in that paper, they use quantum decision theory, basically quantum theory that we adopt from quantum probability that we use. So this is a basic motivation for our work. Why do we need quantum probability here for uh, for um, for modeling the user's information need? Because it has two aspects, that is risk and ambiguity associated with selection of information. Maybe you can check the paper. It's right here, if I'm not mistaken.
Yeah, it's an example of incompatible
Yeah.
observables or non-commutative logic.
So this is the paper, risk and ambiguity in information seeking. This one.
Okay, thank you. Yeah, if there are no other questions, we can move on and ask the next speaker. And I thank you very much, Amit, for his talk.
Thanks for the opportunity to the
Sure.
audience.